record this?
Sure.
Yeah. So I started the recording. It's 2:04, so we should get started. So it's a pleasure to have here today our good friend, Professor Ulloa. Professor Ulloa got his bachelor's in 1979 at National University of Mexico. He got his PhD in 1984 at the State University of New York at Buffalo. And he got his postdoc at Simon Fraser University between 1984 and 1986. And he has been a full professor, or better, he has been at Ohio University, Department of Physics and Astronomy in Athens, Ohio, since 1986, where he is a full professor. That's almost 40 years. That's amazing.
No, sorry.
Yeah, and he has been in many places in Europe and the US and so on and so forth. He's very well known. He came here to Uberlândia many times already. And the title of his talk today is Interactions of Rare Earths, Ions and Complexes on Metal Surfaces. Sergio, welcome. Thank you very much for accepting our invitation, and the microphone is yours.
Thank you so much. You can hear me well? Can you hear me well?
Yes.
Okay. Thank you. All right.
Sure.
So I've been in Ohio University for a long time. I tell people that I started when I was 10, so it's okay. So let me. The other thing is that I thank you for the opportunity to give this presentation. I only wish it was among the mango trees in your backyard or whatever in Uberlândia. But instead, I'm here in Ohio. I mean, the weather is beautiful, but I definitely would prefer the food in Brazil. Anyways, all right. So I'll tell you a little bit about these. What are these rare earth ion and what is the studies that we're working on. This is a collaboration that involves different groups in Arizona State and University of Illinois at Chicago, and especially at Argonne National Lab, which is the lead of this effort is an STM person. I don't know. Let's see if I have a pointer. Do you see my laser pointer?
Yes.
Perfect. Just because it might be helpful. All right. So in the work that I'll tell you here today is mostly work done by my students, David and Abram, and so we're in Ohio. So for those of you who don't know where Ohio is, of course now you know that it is the place where Haitians eat pets. Apparently, I don't believe that. And we are. This is Ohio here. You see, we're bordering with the one of the lakes. Athens is down there in the southeast corner. Springfield, by the way, if you're interested, is somewhere here above the O in the first Ohio. All right. Let me skip this because this is kind of sad. Red is when whoever voted for Trump. You can see that we're blue. This blue lowest corner is where we live. Springfield, I guess, is kind of red too. But anyhow, so we hope that all this will be blue in the next election. We'll see. Anyways, there's a picture of the Athens campus. Here in the front, you don't see, but it's a river that goes around the town. This is a nice spring. It's about this, this would be the panorama nowadays. Here is, I should have let you read this. We're about 30,000 students. There's some, things you can look up on our website. That's the picture of the main building where the president sits. Again, it was the first university established in the what is called, the first territory after the 13 colonies was Ohio, and so that's what the first university is. Anyhow, so let me go back to the main topic. What are rare earth elements? So if you're like me, I mean, you kind of remember these from kindergarten chemistry, maybe. And there is these elements that are typically written at the bottom of the periodic table. And just like you might remember, the first two columns in the periodic table refer to incomplete or whatever s orbitals. And then the last 6 refers to p orbitals. Well, in this middle one are definitely the d orbitals, but of course, occasionally f orbitals come in. And so that's what these guys are. And there's a whole collection. There's 14 of them, of course, which is how many different partial occupations you can have. They all look metallic, as you can tell. Yeah, the name is, I don't really know where the rare came from, but this is what I was telling you about configuration. So there's a list of all these guys along this row, and you can see that they have full shell and then an incomplete F shell, right? So from 1 to 14. Lanthanum will have F0, of course, but it chemically behaves very much like a rare earth. The other thing that is interesting is that they all have these 2 electrons, sometimes, a third one in the d orbital. And so whenever they react chemically, they tend to release these electrons and they get charged, either +2 or +3. And that's a very typical ionic state of these materials. Because they have very similar orbitals in the s, and they're the ones that are released easily, they all behave chemically very, very similarly. And the F's don't matter too much on the chemistry because those F's are very tightly bound to the nucleus, and so they're actually relatively inert, if you will. So, all right. I should have said, by the way, I don't see anybody, but let me tell you that if you have any questions, please speak up or tell George on a chat. He's monitoring the chart, and he'll let us know. Okay, so please interrupt anytime. So as I said, I don't really know why exactly these elements are called rare, but in fact they're not so rare. There's a table that lists the abundance of these elements. You can see the ones that are bold are the so-called rare earths. And surely some of them are not as abundant, say promethium, which is radioactive, of course, or these other guys, lutetium and terbium and so on. They have relatively low abundances, less than 10, say. But in all of these cases, notice they're a lot more abundant, 10 times or more, than silver and gold. So in that sense, they're a lot more common than these guys would be called precious, of course. So and that goes for these other materials. So it's kind of interesting that they're abundant, but they're historically were discovered relatively late because, in fact, their chemistry. It was very hard to isolate them. The other interesting thing about them is that, before I go, the other interesting thing about them is that I don't know if you noticed that they have these terbium, lutetium. They have these names because they were all discovered out of the same mineral in a Swedish Utörby town, and so therefore the names, right? Terbium and erbium. So all of those names come from that, which is, how many times can you use the name of the town to name an element? But anyhow, all right. They're very important as far as uses is concerned. So you can see here's a nice illustration of they're very. Oh, I should have mention that, of course, because they have these incomplete F shells, they're magnetic. I'll talk about that in a second too. But so they're strong, they're very good magnets, and they're used, of course, for many other things, including, for example, the turbines that are, the wind turbines that rotate relatively slowly. These materials are essential to make the electromagnets there work. And so there are many other applications. Apart from their magnetic behavior, they're very good catalysts. And so that's again the chemistry part. And one interesting use is this, that they're actually good phosphors because they have very specific optical signatures. I'll talk about that in a second too. So where are they on Earth? You can see they're all over the place. There's quite a few, here in Brazil. So I guess you guys are sitting on a nice rich mines. And here are the reserves. Notice that China has the most, but Brazil is like third in the world, according to this table. So not bad, guys. So it's a nice richness. I don't know where in Brazil they are, but so it says that you have a lot. All right, let's talk about physics. So these are the ionic radius of the various atoms. So down here is transition metals, chromium, manganese, iron, and so on. And you can see that their radius, once they ionize, is less than an angstrom, right? So 0.6 in this scale. While all these rare earths up here have a relative, much bigger, double the size. And so every time you try to put one of these in any metal, say, then of course they distort the lattice. And so despite that strong or rather large size, they get used in, for magnetic alloys and whatnot. But they form the lattice quite a bit, and that sometimes they're used for that application. The other thing about the incomplete F shells is that these guys are basically the poster children, I guess, for what is called Hund's rules. You must have learned this in I don't know, school sometime, that basically whenever you're having complete shells in an atom, the lowest energy configuration is the one that maximizes the spin and angular momentum. And so you can see that is what this, and in fact, that is the case for these atoms. So that also explains, right, why the magnetic moment is so large, because the overall angular momentum is rather large. And depending on whether you look at the spin, which feels, it has 14 electrons, remember? So as you add one more electron, as you go up in Z, the spin of the ground state increases, as you would imagine. And so that gives you an overall total angular momentum given by this black curve. So very strong magnetic moments. Now, I already mentioned that they have very similar chemical activity, and that because they have very different magnetic moments, they have very different magnetic behavior, even though they may be the same or similar compound, right? So if you have a rare earth in titanium oxide, they will have different magnetic behavior because of this. So they have interesting properties. Let me go back to the optical. So because the F shell electrons are so tightly bound, that means that they're relatively inert with the environment. So and so that also means that whenever there are transitions that involve the F electrons, there are spin transitions, if you will, they will be unchanged by whatever you put them, essentially. And so if you have europium, say in this diagram, it will always, quote unquote, have have a luminescence at about 650 or so nanometers, while erbium will be this green, and thulium and gadolinium, and they're all, it doesn't matter where you put them, you can always use them as markers, if you will. So people do that, use them as labels. You can use them, of course, in lasers, for example, and impurities, neodymium YAG lasers, or they can be used as tags in molecules, or in fact, they're so reliable as far as the wavelength is concerned that people use them as optical memories, and there is conversations about using them as qubits as well. But so they're kind of interesting materials. This is, well, just a proof of those. Let me skip that because it's rather technical. But depending on what is the ion, notice that these are ions, they have very definite transitions associated with their various atomic transitions that involve the F electrons for the most part. All right. They because they have these very peculiar sharp lines, right? Namely, they're not interacting with the environment. They're used in a number of devices. Here is one in a resonator where they fabricate photonic crystals, so-called, right? A periodic modulation of a dielectric that traps the light, and so they can put a particular marker and know that they're exciting that particular atom at that case. And so this is just a generic example of their use beyond, magnets or whatever. It's more specific to the optical transitions. Because the optics is so interesting, so there has been an effort over the years, and still part of our discussions, that you can use these various atoms as in what is called up conversion. And namely, you send a photon, and if you tune the corresponding acceptor and donor species, you can actually generate light that is of higher energy than the one you put in. And so that will be an up conversion. And of course, for that, you need to arrange the atoms to be in a very peculiar order according to their characteristic spectrum, which is illustrated here at the bottom. And one way that people have tried to do that is in these nanoparticles that have very specific composition and dopings, right? So that presumably you'll have this sequence. Part of the problem is that they're not ordered, and sometimes they're not as efficient. And so people are still not as struggling, but certainly trying to optimize this. So, all right. Again, if there are questions, I can talk more about this, but let me move on. All right. So let me tell you a little bit about the specific work we're doing with these rare earth atoms. And in particular, let me start with the idea of depositing these atoms on a metal surface. And the motivation for that is that, of course, as I mentioned, we work in an STM group, right? The sort of the experiments that drive much of this is an STM group, and they are experts in depositing atoms and molecules on metal surfaces. So in particular, we asked the question, what would be the sort of the mechanics or the dynamics of putting rare earths on a metal? And I'll tell you why that would be interesting. There are many possibilities. For one, they're a magnetic object, and so whenever you put them on a metal, there you may want to see whether they actually exhibit condo physics, which George is very fond of, but among other things. So before going there, this is part of the collaboration involves a group that does DFT calculations. And so what I'm showing here in this slide are the results of calculations using this functional for a chain of europium ions, right? These blue, or not blue, purple, or whatever color that is, ions can be thought of as a line of europium. They're deposited on gold in what is called the 1-1-1 direction. So it looks like this triangular array of atoms from the top, right, that you see here on the bottom right. And so you have these europium atoms arranged in kind of a line. You can see that it's not perfect line because, of course, they're sitting on bridge sites, namely, sort of the position right between two gold atoms. That's called a bridge right there. And so these guys don't quite align with each other, and so that's what gives you this zigzaggy kind of arrangement, but that's the equilibrium. And so you want to know what is the charge of these objects. Turns out that this europium, it's stable at about charge 2, which means that they have a magnetic moment, which is rather large, right? 3.5 Bohr magnetons, namely they're objects that have a spin 7/2, and they're in close proximity to each other, so they must be talking, right? Would be one question. Now, this is the DFT results. These are orbitals. You can see that there is a peak below the Fermi level associated with the spin polarization of this, right? Okay, again, I don't see, it's a bad thing about giving a talk to the screen is that I don't know whether I'm getting across or not, but please raise your hand or type out if you have a question. All right, so that's a calculation from DFT. Now, the DFT folks can also consider different configurations of these magnetic species. And, I already said that. And so they can consider, imagine an up-down, where it refers to the 7/2. 7/2 is the magnitude of the spin, so that means that the SZ projection can have 14 different values, right? 7 plus minus 7/2, plus minus 5/2, and so on. And so you can consider different configurations. And in the DFT, consider energy differences between, say, a canonical one where everybody is up, the ferromagnetic, and then look at the other configurations to see which one is lowest. And in this case, you see that the ferromagnetic configuration is the lowest in energy, and the others are a little bit higher in energy. So we can actually extract from this information in a simple model of spins interacting with each other, just what would be these constants, these J1, J2, which will be the nearest neighbor coupling, Heisenberg coupling, and the next nearest neighbor coupling. All right, and so you can write equations that you can uniquely solve for J1, J2. So with this information, you can write. Now you see, all right, I know that these ions interact through the substrate, essentially, probably in some kind of RKKY interaction, and they behave according to these constants. So the strongest interaction is this, is ferromagnetic, as we saw from the ground state, and is nearest neighbors, and it's about 1 Kelvin in magnitude, or if you like millivolts, it's about 1/10 of a millivolt. Now, the next nearest neighbor interaction is anti-ferromagnetic, and so which means that there is a bit of a frustration, if you will, in the chain, just because the J2 is trying to misalign it, if you will. But of course, that is a smaller value, about 5 times smaller than the ferro, so the ferro wins. But it's may give interesting structure, so to speak. And then this Hamiltonian also considers a term, because even though the spins, of course, the atom is fully spherically symmetric, and so there is no preference for which direction is up, if you will. Once it is deposited on the surface, there is what is called an anisotropy. So this is every time you introduce a metal or an object into an environment that has symmetries, in this case is the 1-1-1 surface, then there is potential for breaking of that total rotational symmetry. And in this particular case, the DFT guys have estimated that to be bigger than, so to be in between magnitude wise, between the nearest neighbor and the next nearest neighbor, right? So it's about half a Kelvin. And it is positive, meaning that this energy is minimal whenever SZ is 0, right? Because A is positive. And so if SZ on average, so to speak, is 0, this will be the smallest energy. And that means that even though the spin could in principle be in all directions, the anisotropy pushes those spins to be in the plane. And so that's what is called this easy plane anisotropy. So the A pushes the spins to be down in the plane. The J1 makes them ferromagnetic. So, but they're ferro in the plane, right? So, and the J2 tries to twist them away from that, all in the plane, because this is the one, this, you know, in order of magnitude, if you will, this is ferro, this pushes down, and this tries to squeak him away. So it's kind of an interesting system. And so the question is, well, oh, I already said that. What does it do, right? How can we probe this? Because ultimately, this is a DFT, and so the question, what is the prediction for, say, an STM measurement? All right. So in order to do that, so David, my student, calculated the excitation spectrum. Notice, by the way, that the Hamiltonian that is written is only a Heisenberg Hamiltonian, because we ignore the possible electronic excitations. There are, of course, but they occur at an energy that is much bigger. We're talking about electron volts or fractions of electron volts. Well, as I show you, the J's are correspondingly millivolts, fractions of millivolts. So this is the low energy excitations of the system are definitely spin. All right. So and so we can get away with treating this dynamics by just considering the spin degree of freedom. So this is the ground state happens to be a singlet because of the dominance of this anisotropy. SZ is 0, right? So that means it is a singlet. The spin is 14, namely, I should have said this is a 4-chain, right? Just because we want to motivate this to an STM experiment. And in the STM experiment, they can move around the atoms, right? You might have seen this IBM logo, for example, that was written years ago with atoms. And so they can do that. They can actually notch essentially the atoms with the STM tip into falling into this particular arrangement or another. And so in 4, we figure was like a good size. Is not the longer the chain is, the harder it is to assemble, obviously. And so 4 would be like an interesting middle size to see whether there's anything interesting. So these 4 atoms are ferromagnetically coupled. So think of their 7 halves or adding up. So that means the total spin is 14, right? And because of the anisotropy, they're all pointing in the plane, so to speak. So with SZ equals 0. So and that's the ground state right there, you see. Now the excited states have still total spin 14, but have increasing SZ projections. So the ground state is all in the plane. I don't know, you can see my hands, but as the total spin is in the plane, and excitations basically crank up the state to plus or minus, and then plus or minus 2, and so on. So every one of these doublets you see here correspond to a slightly higher SZ as you go on. These other triplets and whatnot correspond to different values of S. So you can fully, obviously, analyze what are the quantum numbers of these various states, because you have total access to this Hamiltonian. And this is the full spectrum, all right? There's still a lot of states, but you can do, see, this 4,000 and change, but you can do it exactly on the computer. So that's what this is. All right. All this, by the way, is measured in units of the nearest neighbor coupling, all right? So now, how will this connect with the experiment? So this is an experiment done in a different system in 16, you can see, 2016, where they deposited cobalt chains. So here's the analog, right? Why we thought about this. In this case, they're transition metal, and they're deposited on this, which is copper with a bit of an insulating in this case, because there is other issues, but basically they wanted to put it on this insulator. And of course, a description is similar to what we had. Here they only consider nearest neighbor Hubbard. Cobalt has a spin of 3/2, so it's a little simpler. There's magnetic anisotropy, and there is, in this case, magnetic field that you can imagine applying. And so in this system, the magnetic anisotropy is dominant. You can see it's 12 times J. So this is dominated by magnetic anisotropy, and this is a small parameter. Notice that in our system is reversed, but not by a lot, a factor of 2, but it's still J is larger. All right, so what do you expect? In an STM, you can measure the differential conductance, which is akin to measuring the density of states. And so now as they apply a magnetic field, you see the red line corresponds to no magnetic field, and you have a peak associated with the excitations, which in this case will be at 0 energy. Now, as you apply a field, notice that peak splits into 2. And that is interpreted to say that, in fact, even though let me go back. Even though this is a cobalt 3/2 spin, so you would expect 4-fold degenerate for every cobalt, right? So it turns out that the magnetic anisotropy splits the level, and it gives you a lowest doublets only, and that's what these peaks are. Because as you apply the field, one of these states will disperse up in field, and the other one will space down, and that means that around the Fermi level they will result in these 2 peaks. And so depending on the size, this is for an isolated atom, I must say. Now, once you have chains that grow in size, you can see that this splitting, right, that is illustrated here, that is that cartoon up there, gets a little bit more complicated because, of course, you have interaction between the different spins. And so you have a pattern that is associated with the interactions that appear between the different spins. But bottom line, as far as the take-home message, if you will, from this slide for you, is that in fact STM can, by applying fields and applying bias voltages, which is what this x-axis is doing, you can actually explore what is the excitation spectrum of your system. All right, so that's what is really interesting about this setup, that you can actually map it, if you will, by knowing the slows will give you the G factor, these G factors, and then where exactly these transitions occur are a function of the various coupling constants. So you can extract these coupling constants even if you did not have a DFT calculation to tell you what they are. All right.
Sergio.
So what is the case? I'm sorry. Yes.
Yeah. Sorry. What is D?
It's an anisotropy, but it's it's not in this equation. I'm sorry, but it has to do with you. It goes like S directly, SZ individually. Well, I mean, in a sense, it's
crystal field.
I'm sorry. I know why it happens. This D is A. So it's here. It's here. I guess I have an A here, but it should have been A. I'm sorry about that.
Okay.
This D is A.
Okay.
No, I thought it was for a minute that it was a different anisotropy, but it's not.
Okay.
This A is
Thank
that
you.
D. Okay.
Thank you.
All right. So now you in our case, right, that spectrum that I showed, now we can turn on magnetic field as well, of course. And this is what happens. This is the excitation, right, away from the ground state as a function of some magnetic field that you apply. This is the whole spectrum of the lowest states. You can see is a bunch of, it looks like a parabola, but in fact, if you look at every one of them, corresponds to a line that doesn't disperse in field. Here is this SZ0, which was the ground state. It doesn't have a spin, so it doesn't care for magnetic field. And then there is the excited states have different spin plus and minus 1. So they will give rise to this line here and the other line down. So when you take the difference, it gives rise to this behavior, right? So it's just the spectrum of excitations. So we know where each excitation is in units of J1 and what their behavior is in field. Notice that, of course, they cross occasionally, and so you'll have excitations that go down, and then the ground state switches because the magnetic field is enough to make the +1, say, state to be the ground state, and so now the field dependence of the excitation changes. So it's kind of this is a signature of what the spectrum is. This is, by the way, the paper that David wrote. All right. So so we have the spectrum. How do we calculate the DI/dV, which is what we want to compare with experiments? And so it is this calculation. So it's like a spectral function where you consider the ground state of the system, and then you can either think about the physical phenomenon that occurs here is that the tip, and I have a little animation here. Hey, how about that? You can sweep the STM back and forth, sit on any particular one, say, if you want that, and then pass a current. This current can either flip the spin up, right? So increase it as it tunnels through. It can flip it down, in general, or may just scatter without flipping it. And so it is basically something like this. And you have all these events will contribute to the current, if you will. This will be the probability of that occurring. So it will contribute to the density of excitations that you see in the STM, as long as the energy here, this delta function, is appropriate and you're at the right bias to excite basically that state. Okay, and so let me go to the next one. Here is it's a map. This intensity map here on the right tells you that quantity, the differential conductance, we call it, although strictly speaking it's not, right? It's just a spectral function of that tunneling event for either, for the one scattering event. And so you can have, whenever you see whenever the energy of the bias, which is what this axis on the x-axis would be, is enough for that particular field, you'll have an excitation. So this is akin to what I show you from the experiment that had a line. So that's the Zeeman line that you would see, if you will. Now here is shifted at some at some value, but it's essentially that. So these two lines correspond to the excitation of the S equals Z1, if you will, from the ground state. And it occurs at a finite energy value until the ground state switches, and then the dependence switches again. And so this switching every time there is a switch, that corresponds to a change in the ground state, essentially. And there is a manifold that occurs close to zero energy, and there is another one that occurs at 2, because there is the other excitations to other spin projections. All right. And so there is a definite pattern of what you would find, presumably. Again, the separation between manifolds and the spacing between these little braids correspond to or depend on the parameters of the J1, J2s of the system in A's, of course, the anisotropy. Now, if you change remember this is a finite size change of 4 atoms, and you can tunnel into the first or tunnel into the second. And there are some differences, but not terribly large, right? So, because the system is rather small, but you can still tell that whether you tunnel on the 1 and the 2, the environment is different, and so the excitation pattern is different. All right. So let me. By the way, George, I have 1:43. Until what time do I have?
2, if you wish.
Well, I mean, I don't want to.
Sorry, yeah, 2 for you.
2. Okay. Yeah. All right. So 15 minutes. All right. So let me tell you about this. So can we measure entanglement will be the question, right? So we can get all the parameters from the STM. Can we measure entanglement? And so David has been working recently on considering, imagine a triangle like this that is frustrated, namely the coupling between these two is anti-ferromagnetic, and the same with all the three, right? That depends on the distance, so that only the J2, if you will, is relevant, right? The nearest neighbor is, will be much closer. They're distant here in such a way that they're interacting only anti-ferromagnetically. And so this is a frustrated system. And now the question is, all right, let me bring another probe atom, this number 3 here, and provide sort of a polarization for this triangle and explore what happens. So we can calculate the energies, we can calculate the states, of course, and in particular, calculate the entanglement and entropy of the triangle once you remove 3. So it tells you how much entanglement there is here, and entanglement is associated with frustration. So, and it turns out that depending on the distance of the probe, right, how far this is from the triangle, which is this vertical axis, or where exactly an angle, right? There's an angle here. The entanglement entropy changes in a rather, complicated way. So can we actually measure? This is all calculations, but can we ask the STM to measure this? And if you look at this narrow narrow region, small angles, you can see that that's this guy, right? This is distance, this is angles at the 1 degree, so away from the middle, right? So you're at 0 here, you will be along this line, just moving along this line, diagonal. And you can see that if you do that, the entanglement entropy changes to a minimum, and whenever it's green, and then it goes up, and then it goes minimum again, and so on, all by just moving the 3 away. And of course, that changes because as you move it away, the interaction with the different other guys is changing, and so you're monitoring that. And at small angles, you can see it's essentially flat, but you can still ask, all right, what is the differential conductance as I do that, say, along the 0, right? So in any of these angles, so close to this middle line, if I move away, what will be the differential conductance be? And this is what results. So we see that the differential conductance actually, has this very strong dispersion, and it goes to 0 energy whenever the entanglement entropy is minimum. And it goes away, further away energy whenever the entanglement entropy is maximum. So even though we're doing a local measurement of the environment of these ions by doing the STM probe locally, that reflects the entanglement entropy of the probe, right? I should say that this differential conductance is done on one of the atoms here in the triangle. Any of I think is 0 in that case. So, but there is a 1-to-1 correspondence, so to speak, between entanglement entropy and differential conductance, and so which is an interesting phenomenon that we're exploring further. Let me skip this because I want to get to something else. So, all right, changing gears altogether, and actually the main experimental effort in the group is along dealing with molecular complexes. That's why I want to tell you a little bit about them. There are many things that people are doing, but the one particular one, for example, is this. So see, these rare earths are these ionic objects. Remember, they essentially have a +3 ionic state. This is lanthanum. And the chemists in the group make these complexes where they attach these molecules. In this case, this is PCAM, which is all this, I cannot say, right? That guy, which is it's a polar molecule, right? It's got nitrogen and oxygen here in the this purple is nitrogen, and the red is oxygen. So they're very polar, right? They're polarizable locally. And so when these negative charges essentially see this positive charge, they of course get polarized to it and attach and form a complex that is incredibly stable. This is different than the usual, chemistry bonding that I learned in kindergarten, which is it's not ionic because there is no charge exchange. It's not covalent because there are no electrons mediating the bonding. But in fact, it's just polarization. And I don't know what the chemists call it, but to me, this is like Coulomb coupling, but of charges together, right? Just like the balloons on the wall. Whenever you rub the balloon on your head and stick it on the wall, it's basically polarization. There is no charge transfer, and they're very, very stable. They can change the ion here to europium or whatever you want, and then the molecule can also. This is what is used for organic solvents, but it turns out that you can change it to this if you want inorganic solvents, right? Like water, for example. That's called DPIC. Anyway, so these objects are synthesized, and they're not trivial to make, but relatively easy apparently. Here's another picture. Oh, when they synthesize them in solution. So here's europium, for example, the 3 molecules, each of them, this thing saturates to 3 mostly for structural reasons, right? So because there is no charge transfer, you could imagine having more, but just they don't fit around each other. And the equilibrium configuration is with 3. But of course, the entire complex is charged because these guys are neutral, right? Every one of these pCAM molecules is neutral, it's polarized, but is neutral. So the overall complex is still charged at +3. So whenever they make them in solution, there's got to be compensating counterions, so-called, that have negative charge. So there should be 3 of these guys for every one of the molecules. And so that's how they make them in. It's the chemistry of it. All right.
Sergio,
So
those are those lithiums in the
yeah. And this
they are not part of the molecule, right?
No. They're ions. You can put it different. I mean, it's this.
Okay.
I borrowed this picture from the synthesis part, and so they put lithium, this thing, which is a salt, in the solution for it to occur, and then they remove whatever they don't want.
Okay.
I mean, I'm terrible at the chemistry. There's 20 steps, and at the end
You
of
are-
the day,
you are not
have this
alone.
object surrounded by these guys, essentially.
Okay. Thank you.
Yeah, no, sorry. So here is the other thing too, and again, they're couple. They have a net charge overall, and they need counterions. Once you take this complex and deposit it on a surface, this is what happens. This is an STM map of this europium, in this case pCAM, on a gold surface. And you see, I mean, there's a blob, right? It's about 10 angstroms bar here. So that's roughly the size that you expect. And you have this very symmetric blob. It's not perfectly symmetric, so that there is some deformation of this tetrad that as it falls on the surface, but it's definitely there. Here is for the DPIC. Again, slightly, you see this a little bit longer than those 2 sides, but they're roughly similar, right? So you can deposit them on any gold or copper surface, or that's what they do here. So here is another illustration of that. Here's the molecule. Notice that it is a little bit twisted, so that's what is called the spiral. And it is believed that in fact, for the most part, the molecule is not by itself, right? Which will be this pictures up here, but in fact, it has a counterion in under it. and this is just from the pictures. Basically, they've seen so many of these that they can tell when the cluster has a counter ion and when it doesn't. And I'll show you that in a second. So here's an example of that. So here, when they deposit them, so there are these clusters. For example, here there's 4. You can see 4 little pyramids attached. This one is 6. There's these blobs 2, and there is another blob in another one, and 2 more down here, and they have different character. Notice that depending on the bias that you apply, you can monitor these homolumo gaps and take images, right? So these ones in the corner, these guys that look brighter, are indeed brighter, and the other ones are dimmer because you're monitoring at a particular voltage, say around here, so you see one of them and not the other. You see, or definitely this guy is brighter, and that is associated with what is the charge. So either 3 or 2, and whenever it's 2, it's because it has a counter ion. So you can, from the STM, differentiate between the different clusters, whether it's +3 cluster, namely not counter ion, or +2 clusters that have one counter ion under it. So these things are very mobile, and so it's like an ionic liquid because they're positively charged, right? Either +3 or +2. They're sitting on the surface, which provides bonding to the surface, but they are very mobile on the surface. At low temperature, and they're mobile, you can see these blurry images is because as they're trying to take the STM picture, the molecules have shifted. But if you cool them to 5 Kelvin, then they form these clusters like the ones I show you. Sometimes there's 2, sometimes there's 4, or sometimes there's 6. Different complexes, all right? So here's another picture. There's 2, there's 4, and this 6 again. So, and you can clearly identify which complex is which by the appearance, but also by the DIDV as a function of bias. So you can see where are the homolumo peaks. So now the question is there, now these are positively charged, all of them, right? All of these clusters are positively charged. They may have +3 like this guy, or +2, but they're all positively charged. So how come they are attached, right? So that was a question we had. What happened to the Coulomb repulsion between them? And then you say, well, I remember my electrostatics and say I have a bunch of charged objects that sit on a surface, but that means that there is a charge induced right at the interface that can be thought of as an image charge, right, just below. So that reduces the repulsion because, of course, now they're neutral, right? This object is essentially neutral, and because of the electrons at the surface that provide the compensating field, but they're still dipoles. So these are upright dipoles, all of them, and upright dipoles still repel each other. And so much weaker, but they still do. So the screening from the surface weakens the repulsion, but it doesn't cancel it altogether. And you can, strictly speaking, you cannot bind dipoles if they're all aligned. You can bind them if they are able to flip, but these guys cannot flip because the positive charge is always at top. So we ask the question, so is there charge transfer that reduces the ionic charge? And the answer is no, because of, again, these are F electrons that are tightly bound. There is no extra charge transfer, to speak of. There's maybe a fraction, but not. And DFT does calculations and they see no charge transfer. Are there correlation potentials? Because after all, they're sitting on a bunch of atoms. But the answer is no, because they're mobile. Remember that, so that shouldn't be that strong. So counter ions, more counter ions, perhaps to cancel the charge, and there is no evidence of that. So so we push this. You can actually do estimates of this binding, put in numbers, But in particular, so this is a result coming from a DFT calculation. This is a massive calculation where they have two complexes, one with a counter ion, one without, say, to simplify it, and ask what is the binding energy as a function of position, and you can see that there is a minimum that agrees roughly with the experimental value of about a nanometer. So in the conclusion from this, and I don't have time to go into more details, but the conclusion of this is that, look at these closed rings that appear in these molecules. As the molecules bind, turns out that these rings, right, this guy here and the corresponding one in front, actually twist each other and end up stacking. And so even though the interaction between them is not as strong because it's van der Waals, they're neutral, it is strong enough to basically compensate the repulsion that appears from these dipoles. But it is essential that they sit on the surface to actually compensate. And so that's what we explore and just recently published in that paper. So let me skip that. And I don't have time. So yeah, I'm sorry. I run out of time. I could tell you about this if anybody's interested. Let me just go to the conclusions because oops, I came out of that presentation somehow. Am I still sharing?
You stopped the sharing.
Oh, is it sharing still?
No, not yet.
No,
you have
I'm sorry. I
No
pushed the
problem.
forward too much. Let's see. Is it back?
Yeah.
Okay. So that
there
I'm
you
sorry. I had plans to tell you a bit about this orbital gating, but that's a summary of the talk. Yeah, so I lost track of my time. So I think we started maybe 5 minutes late, but that's on me. So anyways, I hope that I convince you that these rare earth complexes are really interesting objects. They form, rafts like this on this picture here on the right, where, the color coding chosen by this guy, this dog bone, you see, looks like a black dog bone or like a tie, These guys are actually two molecules that are attached at the tip. And they can do that too. And so when they do that, they form this arrangement of 6 molecules. Notice there's 1 here, 2, 3, 4, 5, and 6. And they sit in this helix kind of thing, leaving a hole, which is this bright spot. And this is just a raft of these molecules that self-assemble. There are interesting properties that we'll look at. They're all magnetic, remember? Or not necessarily all, but certainly mostly magnetic. So there is still many questions one can ask about possible condos or possible magnetic arrays. It's probably weak coupling, but anyways, that's part of the questions is still remaining. And let me stop here and ask to see whether there are any questions, please.
Thank you, Sergio. Thank you very much for this very nice talk. Rafael has a question. Rafael Costa, please.
Hello, Professor Ulloa. Thanks for the very nice, very instructive and thorough talk. I mean, it's too much to digest, I think.
I know, I'm sorry. Somehow it ran out of way from me. I thought I will finish this like 20 minutes ahead of time.
But it's on me as well that I maybe have not appreciated it all. But can you please go back at the entanglement, your entanglement triangle there, please?
Yes. Let me go back to this. Probably about there. No.
Right. There. Right. Yeah. So I have a couple of questions just to check.
Yes.
At some point, you told us that 0, 1, and 2 are far apart, and then so are you still considering that J1, J2 model with the anisotropy and all?
Okay, thank you for the question, because yes, turns out that once you have J1, J2, of course, you have the couplings at only specific distances. And so, we can go back to the DFT and ask them to calculate for you, but then these calculations are expensive. And so if you ask them from the DFT, they look at you funny and say, go away. But so what we did really is to consider that these interactions are RKKY. So with knowing what is the wavelength of the Fermi wavelength of gold for the surface, you can actually parameterize the RKKY interaction knowing those values that we have. And so what this is strictly speaking, it's a coupling that considers precisely that RKKY oscillatory behavior as a function of distance for any of the ions that are here. So when we put them in the triangle, they're at a distance so that the interaction is the anti-ferromagnetic, right? So that's the distance for J2, say. And now for 3, of course, as it moves along the line, its distance to the different triangle corners will change, and that's what gives rise to this dependence. And it depends according to the RKKY function that we have. Does that answer the question?
Okay. And now the last question is, how do you calculate entanglement? Is it bipartite? You consider the triangle as a entity and the
Correct. Yeah, I mean, you have the state for the entire square here, which is the 4 ions, and then you can project away anything you want, right? You can project the probe, you can project a corner, you can project whatever. And so, so what we project, what this plot is projecting out the probe. Just integrate this out, and so you're left with that, right? Okay.
Now,
but actually, you can integrate out whatever.
Actually, just one more. Is it obvious, or is there a simple intuition as to why is the differential conductance? The next slide, I think. Why
is the
it follows the entanglement entropy?
Correct. I mean, I think that my intuition there is that what the entanglement entropy of the cluster, say, that you remain, is associated with the frustration, essentially, because right, if the system were not frustrated, that would mean that, or I think the inference is almost always true. Let me put it that way. That if it is non-entangled, then the ground state is factorizable, right? That's for sure. But that is also associated with frustration, because that means that you have just a definite term, all right, in your basis, so if you want to call it. And so, and if entanglement is a strong combination of states, that means that when you come locally and ask, can I flip a spin, right, which is what the differential conductance is doing, it would only give you a signal if in fact that possible configuration of a spin flip is in your state. And so that is why, I mean, intuitively, I think there is this connection between the entanglement and the differential conductance. Now, I wish I mean, David is still exploring this, but I think that I believe that is not a quantitative, right? So that, in other words, there is a correlation, but I don't think that a larger differential conductance means more entanglement or less entanglement. It just is. See what I mean? So it's not as quantitative, but I think qualitatively, I think that's there, and it's what I just said.
Right. Just one more. So you're showing the data for small theta.
Let's see if anyone else has a question. If we have time, you can ask further questions. So if anyone has a question, please. So go ahead, Rafael.
Yeah.
I went too fast. I'm sorry.
And now I'm doing the same. So if you look at the entanglement entropy and the differential conductance for larger theta, is this correspondence still there, or is
I think
it
so.
important
No, I
that?
think so. I think so. I mean, you mean this?
Yeah, yeah, yeah.
Yeah. We understand this very beautiful pattern that you see is associated with these nodal lines, for example, here, or minimum, and is whenever, now if I remember right, whenever there is a cancellation of the J's, because the J's, right, the couplings are oscillating, and so whenever you're at a particular angle and particular distance, then this interaction, say, I'm just making it up, between 3 and 1 and 3 and 0 cancel each other out, for example. And then that means that you're not interacting with those, so that actually changes the overall interaction effectively within the triangle, and that gives you a feature. Does that make sense? And so, but it's true that the ground state of the cluster is changing drastically as you move away. Now, we haven't, to answer your question, I guess, we haven't really explored every single line here, but I mean, yes, I don't have the slide here, but I know that whenever you look, there is a feature in the differential conductance associated with dips or bumps in the entanglement entropy. That is, I mean, I cannot tell you, there is not a map that David has done, but whenever we tried different values of angles or distances, there is always a correspondence.
Okay. Now, sorry for making 1,000 of questions, and thank you for your talk.
No problem.
Sure.
So, any other questions? Anyone?
Yeah. Yes, I do. I do have a question.
Yeah, go ahead.
Since Rafael finished all these questions, so my list coming. So, nice talk. Thank you once again for this nice talk.
Thanks.
So I have just a single one. By the way, I have to go taking in a minute. So you have considered the like easy access anisotropy.
Right.
But how
easy
about
plane, but that's
like No, that was DSZ, right?
Right. So in minimum, you see, because it all depends on the sign, you see. So if you let me go back. Oh,
I go to Hamiltonian.
yes. There.
Yeah.
So you see, it all depends. If A were negative, that means that the lowest energy will be when you maximize this.
Fair enough. So the spin will lie on the plane.
That will be easy access.
All right.
The easy access or easy plane just depends on the sign of A.
Right, but what about the transversal anisotropy? Let's say that. But I put that way.
You mean if there is there could be other. In fact, when George asked me about D, I actually thought that was a transverse anisotropy. Yes, people write Hamiltonians with different anisotropy terms, and you could have. I thought you were going to ask me how come there is no Dialosinski-Morilla, right? Because you could have.
That would be my second. That would be my second.
I'm sorry,
question.
I ruined it.
No time anymore.
Sorry, I beat you to it. Yes, no, I mean it is true, and in fact, again, I tried to convince my DFT colleagues to explore that, but that requires a lot more configurations, and you know how it is. When this request came, the student who was working on it was packing his bags, and so that was that. So, but we haven't gone back. We might, but yes, you can imagine putting in different terms in the model and then test the configurations and extract.
Okay.
Yeah, but these were the minimal set of parameters.
It could be there. Okay.
It could be there.
Thank you. I gotta go now teaching. So my student probably.
All right. Have fun.
Okay.
Be nice to them.
Nice to see you again.
Thank you. Thank you.
Sergio, let me, if nobody else is asking, let me ask a couple of questions. So let me try to understand this. This is an effective Hamiltonian that you cooked up from the DFT results. Okay, so they gave you the spectrum and you said, okay, with the up to a certain energy, I can reproduce the result with this effective Hamiltonian.
I mean, just to be precise, actually, DFT,
Okay.
it's a ground state calculation, and so they give you the ground state
Okay.
energies
Ground state.
for different configurations, right?
Okay.
And that's how you extract the J's.
Okay.
But the strictly speaking they could in principle calculate the excitations directly, but in reality the errors in the DFT are too much, right? So they're these are very small energies. They're a tenth of an MeV, and so even you can rely on differences of ground states, but not on direct calculation of excitations.
Okay.
And this is always an approximation too. I mean, this,
Yep.
yeah. So I mean, the point is that the comparison with DFT is only comparison on ground states. They cannot calculate these excitations. I don't know that I can make this definitive, but I believe it's not possible, just at the level of regular DFT.
Okay. There is a question here from Lauro, which probably you met in Campinas. Lauro, Luis student.
Yes. I know who you mean.
Can you see the chat?
See, I get it. Quick question. Is the entanglement differential conductance relation strongly dependent on the form of the RKK-Y interaction? In this way, if the spatial dependence of and then, I don't know, is there more? I mean, the answer...
you are not seeing the rest?
He wrote the question in the public chat.
Yeah, it's in the public chat. I can read for you. In this way, if the spatial dependence of the J's is modified, how would the differential conductance be affected?
Oh, I think that yeah, I mean, okay, I don't know. See, the pattern of differential conductance that exists, say, for this system, right, where the J's are whatever given, the pattern, which is, say, this, where for example, this energy separation between these two bunches of braids is essentially the anisotropy. Because remember, these are in units of J1. Remember, the anisotropy was about half. No, it's the other way around, right? So the point is that the spacing in all the structure you see in the differential conductance depends directly on parameters. In fact, we say in the paper that even if the DFT calculation were wrong, right, or imprecise or whatever, then the behavior will give them what is the precise value of J1 and J2 or whatever. And so you can extract those parameters. So going back to your question, if the precise form of the J's will change, then that will change the spacing between the manifolds, what are the fields at which the braids occur, that kind of thing. So, but you can, I don't know that you can uniquely extract it, but you can certainly try different parameter sets until you reproduce the data. So, and I think that transfers to everything, the entanglement entropy and everything. So it's, I think it's hard, if you wanted to measure the RKKY dependence, for example, in reality, in a system, you would have to see, honest to God, different positions and do differential conductance. But I would do it on the simplest case. So make two guys and then move one of them at different positions and keep measuring. People have done that in experiments. There are some results from Wiesendanger in Hamburg a few years ago, where they actually did it with different atoms, platinum and cobalt and so on. So, but it can be probed directly. But and of course that will change. That will have an effect on these results because it will change the scales. See, all of these, my plots are always in units of the coupling, right? So if you change the coupling, then it would be different. The scale would change. I don't know. Does that answer it?
Yes. Thank you. Thanks.
Okay. All right.
Okay. Do we have more questions? Anyone? So if not, let's thank the speaker again. Thank you, Sergio. Rafael wants to ask another question.
No. Sorry, mistake here.
Okay.
Well,
okay. So
I hope next time it can be in person. Yes.
Yeah. Sure.
All right.
I will be writing you an email asking for the slides so that we can post together with the video.
Okay.
Which will be posted on our YouTube channel.
All right. Okay.
Okay. Thank you very much, Sergio.
Bye, guys.
Nice to see you.
Nice to see you.
Long time, right?
Exactly.
Okay.
Be good. Bye.
Okay. Bye-bye. Thank you. Bye.